Hello and once again welcome to another short video on Graham's law of effusion, some little more advanced aspects of it. Hopefully you already know what is Graham's law of effusion of gases. The rate of effusion is directly proportional to the pressure of the gas and inversely proportional to square root of density or square root of its molar mass. Temperature remaining constant. And you know how to compare between two gases, either having same time of effusion, in that case VA by VB becomes equal to RA by RB, because the rate of effusion is usually expressed as the volume of gas effused per unit time. Or if you keep the volume of gas effused constant, then TB by TA is equal to, and you know, MB by MA square root. Of course, PA by PB will be there because time of effusion has to be inversely related to the gas pressure. The volume of gas effused and the rate of effusion is directly proportional to the pressure of the gas. But we are not going to discuss those initial aspects of Graham's law, its definition and related calculation. But we are wanting to express the rate of effusion in a different way. How the pressure inside the container is decreased with time. So that can be taken also as the rate of effusion. Instantaneous rate of effusion, which is gradually, decreasing. Not that the rate of effusion remains same throughout. Rate is continuously reducing with time. Now, to express the instantaneous rate of effusion, we have to see the instantaneous rate at which pressure is reducing inside the container from which gas is continuously being effused out. Let's see what is the pattern of this reduction in pressure or the rate of effusion. Minus sign stands for as pressure is decreased, time increased, time elapses, time increased, then pressure decreased. So that is indicated by a negative slope. So therefore the minus sign. dP, differential coefficient of pressure with respect to time. This is the instantaneous, you can call it rate of effusion or a rate of change of pressure inside the vessel, is equal to K. K is a proportionality constant. P is the pressure at every instant, which is varying. As time proceeds, the pressure inside also varies, and this is a constant. So K is a constant, root M is a constant. So let us rearrange this equation, bring P to this side and take dt to the right side and integrate from the limits P1 to P2. This is the initial pressure, this is the final pressure, and time from the initial time 0 to time t. So bringing the constant terms outside and integrating, we'll be getting this ln P1 by P2. Since it is a minus sign, then instead of P2 by P1, we are getting P1 by P2 ln. And this is integration dt is t, and the limit 0 to 2 makes this only t. So kt by root over m. So this can be expanded further to give ln P2, bringing ln P2 to the left side one side and ln P1 to the other side. You have an equation like this: ln P final is equal to ln P initial pressure, that is a constant, the initial pressure, and its ln, that is a constant, and minus kt root open root over m. So the independent variable is time and the dependent variable is pressure, and hence here it is ln P2. This is constant, the initial pressure, and hence ln P1 is constant, K and root over m, they are constant. So comparing this to this equation to y is equal to mx plus c, you will find that the graph of ln P is a variable P and T will be giving a negative slope and the slope will be equal to k by root m, and the intercept will be equal to ln p naught. I'm not writing here p1, p naught, the initial pressure, and this is the variable pressure you can call pt. So I simply have written ln p, should have ln pt, because this is the variable pressure. As ln p decreases, time increases, so this is a linear plot, y is equal to mx plus c. And from this you can well say, if you are little aware of the exponential function, you will find that this can be reduced to p2 is equal to p1 into e to the power kt by root over m. Because if you make a ln on both the sides, you will find ln p2, then it will be ln p1, and this will be minus kt by root over m. This power will come outside, and ln e is equal to 1. That is why this will be reduced to its original exponential form. pt, T stands for any variable reduced and reduced and reduced pressure with time, is equal to P naught, which is constant initial pressure, e to the power minus kt upon root m. So the instant rate of effusion follows first order kinetics. You will be knowing in class 12 that such a type of equation signals a style of reaction called first order reaction, where the variable quantity, the y coordinate, will be equal to some constant e to the power minus some constant into t. So this is a first order variation of the rate of effusion or the rate of change of pressure inside the vessel. When we were taking R1 by R2 is equal to M2 by M1 square root, we were not very much interested how the pressure is reduced inside. We were taking the initial time from the beginning, maybe the first part, maybe a couple of seconds we were taking. We were not considering how the pressure inside is reduced, and because of that the rate is also reduced. We don't consider that. We simply ignore all those aspects, that it varies with time. The rate of effusion is not remaining constant. It will vary, it will decrease with time, and not it will remain steady constant. But for the beginners, we only consider the first moments, the few moments after effusion, and see what is happening at R1 by R2 is equal to root over M2 by M1, or if there is a variable initial pressure P1 by P2, we do that. But here we monitor the same gas, how the rate of effusion is decreasing with time. We are not comparing between gases. We are talking about the rate of effusion of a single gas, how it decreases with time in an exponential manner. And that is a fast order decay or decrease process. Now, we will not be interested to solve a problem on this, because that we'll be doing in class 12 in our chemical kinetics program. But what I am interested here in this program is to tell you a problem which will be really intriguing and very interesting. See, read this. If equal masses of helium and argon are placed in a porous container and allowed to escape, which gas will escape faster initially and how much faster? How much faster is important? And what is the mole ratio of helium and argon outside the container at the initial part, that is first few seconds of effusion? Now, you inside the same container, you have two gases, helium and argon, but not in the same mole ratio, because pressure is directly proportional to number of moles. P V is equal to nRT if temperature is constant, volume of the container is constant, so P is proportional to N, not mass. So we convert the masses, equal masses, into the corresponding moles, and these mole ratio is equal to the pressure ratio, the ratio of their partial pressures. More is the number of moles of a certain gas, more is its partial pressure. So that will be taken into consideration. Although the vessel is one, the gases are two, and they have different partial pressures. Had there been a mention of equimolar amounts of helium and argon, then P1 by P2, that term is meaningless. It is redundant, one by one. But since equal masses, then the number of moles will be different because their molar masses are different. And that P1 by P2 will be substituted by the mole ratio is same as the pressure ratio. Now we have found out that number of moles of helium, say X is the mass, X by 4, number of moles of argon, same X by 40, and when you take rate of effusion ratio, then it will be the mole ratio, which is equal to the pressure ratio. So that is the number of moles of helium is X by 4, number of moles of argon is X by 40, XX cancels, and this becomes 10, and as usual this will be inversely related. So this will be 40 is the molar mass of argon and 4 is the molar mass of helium. So root over 10 into 10, because this pressure factor is 10 times more for helium, because the number of moles is 10 times more for helium, and this is root over 10. So it is coming 10 into 3.16, 33.3. So the rate of effusion between helium and that means helium will effuse 31.6. I'm sorry, here there is a mistake. 31.3 times 6 times 31.6 times faster than argon. Can you imagine, had there been no pressure difference, no mole difference, equimolar, then this term would have not been there. It would be 1:1:1. So as usual, as a lay initial beginner does not include the pressure factor, he or she will say that helium, being a lighter gas, will effuse only 3.16 times root over 10 times faster than argon. But now due to greater pressure, 10 times greater pressure effect, helium now will effuse 31.6 times faster than argon. And the initial, whatever is the rate of effusion, same will be the initial composition of the two effused gases outside. Initial. Because inside, when the pressure will drop, the amounts will drop, and then rate will drop, then the ratio will also change. You have to again take into account the new composition inside. So new pressure inside, and then freshly calculate. That will be doing within a short time to discuss about the enrichment of a certain compound in a mixture through gaseous diffusion process. Now here, the outside, in the outside of that effusiometer or that container, in the initial few seconds, if you analyze, inside it was in the ratio of 10 is to 1, 10 is to 1. This is 10 is to 1 ratio. The pressure ratio, the mole ratio was 10 is to 1 inside. But outside, within a few seconds, initially, the mole ratio is 31.6 is to 1. Accordingly, you can find out the mass ratio, which is not required here. The mole ratio is 31.6 is to 1. So whatever is the rate of effusion, initial rate of effusion, same will be the initial mole ratio of the gases which are already effused outside. Is it not interesting? Now, the final thing comes here. the enrichment of a single gaseous component by repeated diffusion steps. It's called atmolysis. You have two gases. You want to carry out a number of diffusion steps, one after the other, and you only collect the first initially effused sample. After few moments or few seconds, you collect it and reject the rest. Take that small little collection outside to another diffusion steps. Perform the diffusion and collect again a few mixture diffused outside, and you will find continuously the lighter component will be enriched in a very slow and steady manner. If the mass difference is small, you may need hundreds of diffusion steps to arrive at the desired level of enrichment. That happens particularly in our atomic reactors, nuclear power plants. We need uranium-235 isotope, not the useless uranium-238, which is present in large quantity. 99.3% is the useless uranium-238 isotope, and only 0.7% is the useful uranium-235 in any natural uranium ore. But the fission cannot be done easily with such a low percentage of the fissile nuclide uranium-235. Or some reactors which need the enriched uranium, where you will learn ordinary light water used as a moderator and a coolant, that particular reactor needs enriched uranium to the extent that uranium-235 contained will be maybe 5 mole percent, 3 mole percent. So how to increase the mole percent from 0.7 to 5 or 3.5 or 6? Of course, if you are wanting to prepare an atom bomb that was dropped on Hiroshima and Nagasaki, those are the uranium bombs and plutonium bombs respectively. There, the 235 content of uranium is nearly 100%. That is for a catastrophic purpose of making deadly nuclear bombs. But for power plants, electrical power plants, nuclear power plants, we need only 5 to 10, maximum 5% enrichment is required. How to do that? So the theory, let us discuss about the theory. Supposing this is the original first vessel containing the two gaseous substances. One is say 235, the other one is 238. And so let's presume that A is a lighter component, B is the heavier component. And if you perform the effusion for some few seconds and stop further effusion, reject this, we don't bother, and you will find there will be a little bit enrichment of the lighter component, and we will find that. And again, you allow this to effuse through a very small orifice for some few moments and collect this. You will find the A will be further enriched. You continue to perform this operation X number of times, you will find that at some stage you have achieved the desired level of A, which is the lighter isotope. I was talking about uranium-235. So let's say NaX is the number of moles that you require for the lighter component, and NBX, ultimately the 100 minus that will be the mole of the unwanted isotope or gas. You wanted to enrich gas A, right? Now let me tell you ready-made equations, and I will explain to you the logic, the derivation behind this equations. Now, for a single step effusion, we write F prime, which is equal to rate of effusion of A by rate of effusion of B, which is root over mb by ma. This is ordinary Graham's law. You might be wondering why I am not using the pressure effect here. Wait, you will find the pressure effect embedded in all these equations. We are taking only molar masses and ignoring the pressure here, because you might argue with me that since one of the components is in 99.3% mole, then the pressure ratio will be also 99.3 by 0.7. Well, you can say that, I don't deny, but just listen how this ready-made formula will help you. This is a single step effusion that is only taking the molar mass into account, the normal Graham's law. Then overall enrichment factor that you need is only F, not F prime. Because you started with Na and Nb, but you want, supposing you want 3% of A. So this NaX is 3 and 97 is B. So the final mole ratio that you will need, that ratio divided by original starting mole ratio of the two, that ratio of the two ratios is called the overall enrichment factor. This is the mole ratio desired. This is the mole ratio originally you had. So the ratio of these two ratios is called the overall enrichment factor F. Now, how to find how many successive effusion steps you have to carry out? Third one, F, the overall enrichment factor F is equal to the single stage effusion enrichment factor F prime to the power X. X is the number of effusion steps, successive effusion steps required. And if you put log on both the sides, then log F is equal to X into log F prime. So X is equal to log F by log F prime, that you will find out the number of steps required. But one thing you have to bear in mind, that every effusion step has to be done for a few moments. Because as you know, the rate of effusion is gradually decreasing in a very systematic and very rapid manner following the first order kinetics like this. Only a few seconds you have to perform the effusion and then stop, reject whatever residual gas mixture is there. You just throw it out and go to the next chamber. Then perform the same, collect some few moments collection outside the third chamber and reject the second chamber, and you continue. You will find this. Let me now explain how do we get these interesting formula, ready-made formula. Have we not included the pressure effect? Have we ignored? No, we have not. See, supposing we consider the first step, only first step. We take the mole ratio, we take the mole ratio as pressure ratio Na, and Nb is the mole ratio of A and B, which is same as pressure ratio. The type of problem we did for argon and helium and argon, and Mb by Ma. So this is the rate of effusion or the mole ratio outside, few moments outside. So here you get the ratio Na1 by Nb1 is this. Now let us consider the second step of effusion, going to the third chamber. So this one, Na3 by Nb3 is, its previous one is Na2 by Nb2 into root over Mb by Ma. But already we know Na2 by Nb2 is equal to this, is equal to this. Is equal to this. Na1 by Nb1 is equal to this. So in place of Na1 by Nb1, if you put this, then this will be doubled. So it will be square of this, and you have only one ratio, that is the initial ratio of Na and Nv. Again, the third step, this is the second step, I'm sorry. This is the first step going to the second chamber. This is the second step going to the third chamber. This is the third effusion going to the fourth chamber, Na3. Now see, this is the third chamber, you are going to this fourth chamber. Na3 by Nb3 is equal to, the previous chamber is Na2 by Nb2 root over Mb by Ma. And if you put this value here, it will become again Na by Nb and Mb by Ma square root to the power 3. And in this similar manner, if you go to the fourth effusion, fifth effusion, xth effusion, you will get the same kind of thing, that NaX, this is the final enrichment level that we want. NaX by Nbx is equal to Na by Nb root over of Mb by Ma square root to the power x, in the similar manner, right? So the pressure term has been taken, and for one, that is why if you bring this to the left side, so NaX by Nbx is the desired mole ratio, Na by Nb is the initial mole ratio, that we call F, the overall enrichment factor F, and this inside the bracket we call F dash, the enrichment in one step, in single step, and this to the power x is the number of steps required. So we have not ignored the pressure effect. Pressure effect is there from the beginning, and that initial mole ratio is remaining, and the next makes the power of Mb by Ma square root more and more. Ultimately we reach this. Therefore we have made a very ready-made cozy formula, as if somebody will have a question, where is the pressure effect? Pressure effect is here in all these derivations. Pressure effect are here, and we land here with this ratio. A ratio of the two ratios is called the overall enrichment factor, and a single enrichment factor is only this, and x is the number of effusion steps. Now I'm taking a very interesting example, that in natural uranium ore you have only 0.7% U-235. I was talking about that, and the rest 238, which is useless. In power plants we need only this one. This is fissile. It can be fissioned by slow neutrons and produce energy. Uranium 235 cannot be 38 cannot be fissioned by slow neutrons. Is useless. So we want to enrich to 6% for our power plant. Say for example, I'm not saying the power plant at Tarapur is wanting this. I'm saying, supposing we want an enrichment up to 30% to make it a nuclear bomb. I'm just kidding. 80% to make it a nuclear bomb. I'm kidding. We need only 6%, from 0.7 to 6% enrichment we need. Now how it is achieved? It is achieved by first preparing their hexafluorides, uranium hexafluoride. By treating the uranium ore with fluorine, you get the corresponding hexafluorides. But there will be two types of hexafluorides. One is uranium 235 hexafluoride, and the other one is uranium 238 hexafluoride, and its molar mass will be more. How many units more? It will be 3 units more, and this is uranium 235 hexafluoride. So take the mixture of these two hexafluorides and start your journey, successive operation steps in the way I told you, and let's see how many effusion steps you have to do, and can you do it? Is it so simple? Let's see. The first, in a single step effusion, what is the enrichment factor Mb by Ma? That is 352. If you add this 238 plus 19, 6 114, you will get 352, and for uranium 235 hexafluoride you will get 3 units less, 349. It will be coming 1.004288, and a lab student, without knowing its significance, just he will ignore all these digits after 1, because there are 2 zeros. Then it will be very, very catastrophic consequence. Log 1, you know what is the value of log 1. So that is why you have to take at least 3 significant digits after the decimal point. Now the overall enrichment factor, we need 6 of 235. This is the lighter component, and the remaining 94 of 238. So this is the ratio mole ratio of the desired enrichment, and the original mole ratio was 0.7 by 99.3. So this comes to 9.05. That is the overall enrichment factor that we need, F. But in a single step, we get this. So you know log F is equal to x into log F dash. This derivation we have done. From here, we know we can make it log here. Log F is equal to x log F dash, F prime. So we have used that equation. So x is equal to log F by log F prime. So that comes to 514.88. So approximately 515 successive effusion steps you have to do so that you can enrich uranium-235 isotope, which is your requirement, from 0.7 to 6%. Is it not interesting? Have we lost any logic anywhere? And this video was meant how the pressure effect is important in cases like this, in studying the rate of effusion, the instantaneous rate of effusion, how it changes gradually. It decreases in an exponential manner following the first order kinetics. We'll be doing those problems later in our class 12 program. Since it is a public video now, if anybody watching and up to end, you never ever hesitate to hit the like button, and also to share with your friends. And also, if you have not subscribed, is there any cost involved in subscribing to any channel? Don't have the wrong impression that subscription means in this case is giving some money or donating some money. No. Just you have to hit the subscribe button so that you are a subscriber to my channel. Bye. Give your comments.